so they decided to postpone.
Hi, I'm Max Donath, and I want to welcome you all to our seminar series on advanced transportation technologies. I'm going to start off by introducing Hannah Grun, who will go through some housekeeping regarding the seminars and everything that's going on here, and then I will come back and introduce our speaker today. Hannah?
Hi everyone. First of all, if you are a student who is enrolled in this course and you've turned in a write-up to me, please check in with me after the seminar and I'll get that back to you. Today we have an audience both online via YouTube and a live audience as well. So for the people who are watching online, please sign in on the chat box in the upper right-hand corner. We are required to report our viewership rates to the US DOT, so we'd be really appreciative if you could tell us how many people are watching from your location. For the live audience, there is a sign-in sheet on the table over there. I'll circulate it around the room, so please make sure you sign in. For those of you watching online, please enter your questions for the presenter in the chat box as well, and we'll read them in the room when we get to the end of the presentation. For the live audience, please hold your questions to the end, and we'll be using these microphones so the webinar audience can hear, so please make sure to hold them pretty close to your face also. That's all.
Well, I'm really honored to introduce our speaker today, Todd Humphreys. He's an associate professor at the University of Texas at Austin and directs the radio navigation lab over there. A couple of things. His specialty is in detection and estimation techniques, signal processing, all related to satellite navigation and autonomous systems. He's been most interested in secure perception for autonomous systems, looking at navigation, timing, and collision avoidance. And his specialty is in the whole area of centimeter accurate locating services. He received the University of Texas Regents Outstanding Teaching Awards in 2012, NSF Career Award in 2015, and the ION, that's the Institute of Navigation's Thurlow Award in 2015. He comes to us originally from Utah State University, where he did his bachelor's and master's, and then went on to Cornell, where he received his PhD. And he's been at Texas since then, I believe. Interesting that Todd was a stage magician for kiddies as a way back when, and he tells me that that's why he's won all these teaching awards. He's learned how to deal with the kiddies in the audience. So anyway, without further ado, we're very pleased to have Todd speak to us.
Great, thanks Max. I'm glad to be here, and my interaction with several of you today has taught me that this is the right institute for this talk today. In fact, I don't know if there'd be a better audience in the world for what I want to share. You already have philosophical leanings toward wanting to have better GNSS, GPS precision on vehicles and so forth. So as Max mentioned, I grew up in northern Utah, and like many of you, I had the experience of needing to get somewhere quickly. I was late for a class or something, and I would just scrape off a little part of the windshield, or maybe stick my head out the window and drive because I didn't want to wait for the defrost to work. And I'm sure you have had these experiences. But when I look at the latest research in autonomous vehicles and I see them talking about the challenges of structured and unstructured roads, they usually put out pictures like this, where they say that this is a snowed-in road, and this one is an unstructured road because it doesn't have any signs. And these all look fairly highly structured to me. And I'm wondering in the back of my mind whether they've really ever driven, say, in Minnesota or northern Utah, or where I did my PhD in Cornell. This is a real challenge, dealing with the vicissitudes of weather and doing this autonomously and reliably. The kind of maps that, say, the Nokia HERE people are thinking of are different from the maps that we've been using so far. These are digital maps. They have lane-level knowledge. They have directions on each lane. And you can get even more precise than this, building up a map through the LiDAR data. And this is one of the HERE vehicles, and I know Max knows quite a bit about this. This is their latest incarnation of the vehicle. It's got visible light sensors. It's got a nice GPS antenna here on the roof, and also LiDAR data. From this, they can make these exquisite three-dimensional maps, and they talk of these maps as an additional sensor. They say you need your LiDAR, you need your visible light cameras, you need other sensors, radar, and etc., but you also need the maps. They're an additional sensor. They allow you to see further down the road. And I like that mentality. Of course, knowing where you are within the map can be done two different ways. You can locate yourself, say with GPS, and assume the map is registered to the same coordinate frame, and now you're in the map. Or you can use simultaneous localization and mapping techniques to either develop the map on the fly or add to it on the fly and locate yourself within the map. And what I'm noticing among Google's and other advanced autonomous cars is that they're opting more for the former. That is, they're opting to marginalize the GNSS sensor and simply use these simultaneous localization and mapping techniques to locate themselves within the map to about 10 centimeters. And everybody, for everybody, the holy grail is decimeter accuracy. You don't need much more than that for the purposes of autonomous driving. And I say that the GNSS receiver has been marginalized on fairly good empirical grounds here. From a recent highly cited paper, the authors of an autonomous vehicle paper said GPS has limited resolution. What do they mean by that? This sounds like people who don't understand GNSS. Limited resolution, they're probably thinking of the 3 to 5 meter errors that you get out of standard positioning service. But GPS can give you centimeter accuracy under the right circumstances, and you can make this fairly ubiquitous if you have enough funding. And it's not really a question of cost in their minds right now, because they're all driving around with these Velodyne sensors on the roof, which are around $60,000 more. So I don't know what they mean by GPS has limited resolution, except that they don't really understand the technology. And then they say the difficulty remains that as GPS is unavailable in many places. That's true, but it can be made more available in those places, probably much more than they think it's available. And connected with the other sensors on the car, it can be made basically as a continuous reference. Also, another index to this marginalization of GPS, GNSS, the organizers of the China Future Challenge, which is like the DARPA Grand Challenge in China, in 2010 forbade the use of GPS. They said, as part of the rules, no GPS. You can't use it except for the overall waypoint location, but you're not able to use it for lane decisions. And I thought that was kind of curious. I'm not sure if the later ones, they've had one all the way up to 2014, if they are also forbidding the use of GPS. But it's the case that these autonomous vehicles are leaning heavily on the Velodyne sensors, heavily on visible light cameras, so much so that the first 8 finishers in the China Future Challenge in 2014, just last year, the first 8 finishers all came across with a Velodyne sensor on the roof. And Google's autonomous cars also use Velodyne sensors. Something I learned just recently, just last week, was that the Google autonomous cars don't have any fancier GPS than your smartphone does. They're using standard positioning service GPS, 3 to 5 meter errors, and they're relying much more heavily on their LiDAR sensors and visible light sensors to do all of their location within the map. All they need is something good enough so that the map is on the right reference frame, and then they can average out the errors as they're moving along. So my main claim here, I'll get to in a bit, can be catalyzed by this discussion that I had with a Daimler engineer just 2 weeks ago. He was talking about Daimler's, and Daimler makes Mercedes and others, Daimler's approach to autonomous systems, autonomous cars. And I asked him, with such an emphasis on visible light sensors for lane keeping, how will your cars react to snow-covered roads and heavy rain? Daimler at least has made the step that they want to depend quite a bit on radar, because they like the fog penetration and the ability to penetrate through rain. But they still depend a lot on visible light cameras, regular cameras, for lane keeping. So I put this question to him, and his response was, our autonomy strategy does not cover these cases. The car will instruct the driver to take over. And basically he says, we don't do that. And that means that for people in Minnesota, during many months of the year, you just don't have a solution from Daimler. And you might not have one going forward, because the way they're constructing these cars so much around the LiDAR and the visible light sensors, and radar in the case of Daimler, is that they're not really opening up the option to rely more heavily on GNSS. But my thinking is that, if this is what you're seeing out the windshield, you better not be too dependent on your visible light cameras. And I would like autonomous cars to have better, not just as good as human, but better driving performance, better security, better safety than humans. And so even if you can't see out the window, I'd like the car to be able to autonomously navigate correctly. So my main thesis statement here today, the one I wish to defend, is that sub-decimeter accurate, low-cost GNSS positioning. GNSS is this umbrella term, Global Navigation Satellite Systems. It's GPS for everybody. Is key to improving the reliability and percent availability of autonomous driving. I don't want for any state in the United States or any province in the world for them to be sort of off limits for many months of the year to autonomous driving. Let's build a solution that works a very high percentage of the time in a very high percentage of the world. And to get here, I'm going to be talking about the research we've been doing in our laboratory to bring the cost of centimeter accurate positioning down. Now you might ask, why is a research laboratory trying to lower costs? That sounds like a startup or a Taiwanese company or something. Well, the truth is that there's a lot of interesting research that can be done asking the questions, what would it take to get from $5,000 receivers to $50 receivers to $5 receivers? This has already happened inside your cell phones. We worked back in the early 1980s with many tens of $1,000 receivers, and now the chip that you have in your phone, probably Broadcom, maybe Qualcomm, is less than $1. Less than $1. It's an enormous pressure that the mass market puts on things to commoditize them. I'd like to see something similar happen to centimeter accurate GNSS, to carrier phase-based GNSS. Today, positioning is used for all sorts of fun applications. Where it's going, I see it going into virtual reality. This is one of the things that we're most interested in my research group. This means that you untether from your computer near your desk and you can walk outdoors and have what we call the physically immersive virtual reality experience, where you're actually in the environment that's being represented to you virtually. So if you see a rock, you can kick it and it's there. You see an avatar, you can hug it and she's there or he's there. This physically immersive stuff wants to have centimeter accuracy. Augmented reality is already being used in, this is the America's Cup here, and mapping, and of course in autonomous driving. All of these applications want precision, and precision is addictive, and so as soon as they get a taste of their centimeter accuracy or decimeter accuracy, they're going to want it always. The improvements to standard positioning service, GNSS, have slowed down. Over the last decade, we got better, especially there was a big jump in 2000 when they turned off so-called selective availability, but we've sort of slowed our pace of improvement, and much of what remains is fundamentally there. It's the multipath errors in the code phase positioning. It's orbital and clock errors that have been diminishing, but not much. And then finally, atmospheric errors, the ionosphere, the troposphere. So you can't do much better if you're going to stay with this paradigm of so-called pseudo-range-based or code phase positioning. Instead, you must look to the carrier phase. I'd like to see us go from lane level, or what we can kind of approximate as meter level, 2 meter level we've got today, down to being able to navigate the wrinkles in the palm of your hand. And for that, we'll have to depend on the carrier phase techniques. The carrier phase-based positioning, instead of using the coded signals that are sent down, they have maybe 2 megahertz bandwidth, maybe 20 megahertz bandwidth, depending on whether you've got the access to the military signals. These kinds of ranges to the satellite are the original concept for GNSS GPS. Back in the early 1980s, though, some folks at JPL and at MIT realized that we could use the carrier phase, which has a wavelength of about 20 centimeters, and locate ourselves to 100th of that. The only challenge being then, which hump am I on? Which phase interval am I on? So the basic idea of carrier phase is you're paying attention to the sinusoid connecting you to the satellite, and the way to figure out what hump you're on, you can do this in a number of ways, but mostly it's a relative technique, it's a differential technique. You've got some station for whose position you know, and then you determine your location relative to that to centimeter accuracy. This is already used and has been used for more than 20 years. And Max was telling me earlier about some of his early uses of this in the late 1990s for tractor trailers, lane keeping and plowing and so forth. This is the key to high yield agriculture now. And what I'd like to see, and of course in surveying, what I'd like to see is also this technique being used in the mass market for smartphones. And that's where we're headed. So the overall strategy, I want to spend some time on this slide because I want to give you a sense for the kind of reorganization that will have to take place for us to support carrier phase accuracy in all of your phones and for your virtual reality headsets and so forth. The basic idea is this. We believe that users in the mass market are going to be sensitive in two primary ways. One is the time to first fix. That is, how long does it take me to get that centimeter accurate position? And currently, I'll just let you know, our experiments in Texas are upwards of 400 seconds to get it onto the cell phone. And I know that many of you are not going to be that patient. So we're looking at ways to bring that down. We think 30 seconds is what could be tolerated by the millennial generation and others. We also think cost is essential here, bringing down the cost to where it's nearing the commodity costs of our Broadcom, Qualcomm chipsets. So these two, if I'm going to bring down the time to fix and cost, what does that mean about the reference network I need to compare my corrections with the reference connect corrections and do this differential positioning? Well, the corollaries here are that as compared to traditional PPP, we believe that network RTK and PPP RTK have faster convergence times, and so they will be kind of the techniques that will be used here. And it will be a different kind of economic paradigm. As the number of users increases, right now they're agriculture users, they're survey users, but they aren't you. They aren't the mass market. They aren't everybody. But they could be. And I think the way to the mass market is probably through the automotive sector. You'll have this on your cars first and then your phones later on, or maybe your virtual reality headsets. But as we expand the number of users, it starts to make sense to densify the network to offset the deficiencies in the low-cost receivers. So as you go to lower and lower costs in the receivers, your antennas get lousy, and you don't necessarily have all of the processing required to do multi-frequency GNSS. So you're more dependent on a close reference station so that you can eliminate the ionospheric and tropospheric errors. So I believe that, if I could save just $1 per receiver by doubling the density of my reference network, maybe that makes sense economically at a certain number of users. And that's something that people who manage the cores network, like Nathan, they can see forward to that time. But right now, the interspacing between the nodes on the cores network here in Minnesota is around 38 kilometers. So it would be more than a 4 times doubling of the density. And yet at that point, we could start to support you all on your phones or on cheap devices. I'm talking $20, $30 devices. And that could revolutionize this space instead of $2,000 to $5,000 devices, which we have currently. So a couple of questions. And I'd like to focus first on the smartphone, just to show you, we went all the way to the worst possible situation, GNSS positioning within a smartphone. We wanted to know what's possible there and how can you deal with the deficiencies of the smartphone environment. What are the primary impediments to centimeter positioning and how can these be addressed? First of all, I just want to do an existence proof, though. This is fairly recent. This was done for the very first time in December. And I believe it's a world first. This is the first time anyone has ever publicly discussed. I'm not sure about what could have been done at the NSA or wherever, but anybody has publicly discussed having obtained a centimeter accurate solution on the antenna, the internal antenna and internal low noise amplifier of a smartphone. This is a Samsung phone. Samsung is working with us on this. They gave us the phone. We tapped off the radio frequency feed just after the low noise amplifier and filters inside. And then we siphoned the radio frequency analog signal and digitized it and then did our own processing on it with an offline software-defined receiver. Why did we do that? Well, because we built that software-defined receiver and we know exactly how it works and we know that it can push the signals farther than the internal chipset. We were also leveraging a higher quality clock, I will admit, than the clock on the inside of the phone. But anyway, world first, we got this cluster of points, that's actually 500 points, taken once per second for these several minutes. And those points represent a solution that's about 2 centimeters absolutely accurate. So the actual antenna location is a little bit to the right, over about 1 centimeter. And then this little corner you see here is a surveyed location of a piece of black tape that I put down on the little tray that we had. I surveyed that location with a nice geodetic grade antenna, and then we were able to locate that cluster with respect to the Earth-centered, Earth-fixed reference frame and position it on the photograph as it was supposed to be. So we were only off by a couple of centimeters using this extremely terrible antenna. And you might be thinking in the back of your head, if you're RF people, you might think, but that's a fine backplane you've got there. It's metal, and it's not going to work so well when you're holding it out. But in truth, it doesn't work too poorly. My student Ken here, who did a lot of this research, Ken Pacina, and just graduated, he's holding the phone out and did so for 5 minutes while I was taking pictures. And the movements that you see here are the movements of Ken's hand. You know, you're not actually able to hold something perfectly steady for 5 minutes, especially when your advisor is taking pictures of you. And 2 or 3 of the signals were passing through Ken's body, so they were also shifting the carrier phase of the received signal, and yet we were able to hold on to it with I should say, no cycle slipping over this interval. One of the evidences I have of this is the plot of residuals you see up here. Time is on the x-axis, and the difference between where the phase of the received signal arrived and where the phase center of the antenna is manifest here. You can see that this y-axis is denoted in millimeters. So our residuals were actually plus and minus about 10 millimeters 1 sigma. Not too bad, not too bad, given the quality of this antenna. So this is another world first. I mean, it happened just after the other world first on the same day. But it shows you that this is just barely possible. And yet the caveat here, the asterisk, is that it took us about 200 or 300 seconds just for this solution to snap in, so that the so-called integer ambiguities that are key, whose resolution is key to getting this kind of centimeter accuracy, could be properly resolved. And that's too long. 300 seconds is too long. It's 5 minutes. And I know that you'd all be too impatient for that. I invited a model to come up. Actually, it's just my wife. But I told her she could come and model for us, and she accepted. And her task was to do what's called light painting. So this was something that Pablo Picasso pioneered back in the 1940s. He would take a burning lamp and a long exposure and paint without being able to see it, but just imagine it in his mind. And she practiced with the special vase. And anyway, she got up there, it was cold. I'm just going to do a star. But that star, to a couple of centimeters accuracy, is exactly how that phone moved. And you can imagine the kind of social interactions you might have if you had this accuracy on your phone, where you could paint a note to your friend on a wall or something, and then that friend could come later and hold up the phone and see the note that you painted. You know, leave a tag on something. The accuracy might be used in ways I can't even imagine. Anyway, Fatima was kind of proud of herself when she got on the cover of GPS World, which is, you know, the big publication in my community. And it's the first time, so far as I know, that they ever did a pink orbit around the O on GPS World. So that's, you know, gave it the feminine touch in a very male-dominated community. So something you may have noticed about these residuals were that even though they were somewhat well-behaved, they were quite large. If you've taken a look at double difference residuals, you know to expect something more on the level of a couple of millimeters. Here's what happens if you're comparing the double difference residuals or looking at the double difference residuals for a nice antenna, the kind that you might use for surveying. The standard deviation, 1 sigma here, about 3.4 millimeters in the double difference. That's between 2 high-quality antennas. What if you go from a high-quality antenna to an abysmal quality antenna, to one that's like the ones inside this Samsung phone? Well, the residuals just blow up. This is the same scale here. And you get very large excursions. This yellow trace goes off and stays off for a good fraction of an hour. What was going on there? Well, this is what's called multipath. Because the antenna is linearly polarized, it can't resist taking in signals that bounce off the ground or off of walls, and it looks to the antenna like those are authentic signals from the satellites. Even if you exclude the worst outliers, which you probably could with a machine learning technique, you're still dealing with 8.6 millimeters in variation. And this is the variation, this is exactly the thing that extends your time to ambiguity resolution. because it takes a while for the satellite to move across the sky so that these residuals look enough different from the errors caused by ionosphere and troposphere, and so that you can basically snap into those positions, the finite discrete positions that you have to choose from. This means you're dealing with a 5-minute wait, whereas over here, if you just had this kind of precision, it would be basically instantaneous. Okay? It's a short baseline. So we understand there are many multipath mitigation techniques. I've got a list of them up here. These don't really apply in this new world where we're working on the phone, inside the phone, because they need good antennas, or they need extremely wide bandwidths. And on the phone, you want to minimize your processing power. So much of this didn't apply. But on the phone, you also have some different options that you don't have with, say, a stationary receiver or one that isn't a phone. So we thought to ourselves, okay, let's take advantage of the unique features of the phone. One unique feature of the phone, by the way, is that it's so easy to move. And when you've got it out in front of you, it wouldn't be much trouble to ask the user to do this. And why would you ask the user to do that? Well, it's because these multipath errors caused by the signals bouncing off things in the environment are highly time correlated over hundreds of seconds. So if you keep the phone stationary like this, you kind of have to wait 100 seconds for that multipath to grow and diminish and grow, and so that you could average and get a zero mean. Okay? But if you just move the phone about wavelength scale random motion, they grow and diminish and pass through zero, and you can take an average over just a couple of seconds and get that averaging down. So you actually increase your unit information per unit time into the estimator that's trying to do the solution by dithering the multipath with this purposeful motion. It basically decorrelates the multipath and increases the information content. Now there's a penalty to be paid for this. In a Kalman filter associated with a static antenna, you can tell the Kalman filter, you're static, you're not moving, and that helps to constrain things inside the filter. When you're telling a Kalman filter or a sequential estimator, whatever you want to call it, that you're moving in some way and you don't know exactly how you're moving, then that weakens its a priori estimate of its location or its trajectory. So you've got these two competing phenomena. On the one hand, you like to move because that increases the amount of information coming in. But on the other hand, you'd like to remain stationary, at least have a good model of how you were moving, so that you don't dribble out that information from the holes in the bucket, you see. And turns out that this competing trade-off works such that if you're dealing with very high quality antennas, the geodetic grade antennas that Nathan has in his 138 node beautiful Minnesota network, you don't want to move them. Leave them be, because their multipath is small enough that you pay more in the penalty than you gain in the information by decreasing the decorrelation time of the multipath induced errors. But as you decrease in the quality of the antenna, going from geodetic grade, dinner plate size, to survey grade, small plate size, down to a patch antenna, down to the antenna in your phone, there comes a time basically between the high quality patch antenna and a low quality patch antenna where it makes sense to move. And it didn't in the past. You talk to a surveyor and they'll say, what, move? I just put the stake down and I wait. And I wouldn't want to dither the antenna back and forth. But when you're talking about really low quality antennas, it does make sense. So you can see here an example of these residuals in a static scenario. You can see how long those time constants are. And then as we move, the time constants get down to below a second. It's very fast. They decorrelate very fast. So the basic idea that we address in a paper we just submitted for review is to do a full analysis of this and find these breakpoints, a full analysis in simulation and also analytical reasoning, to take a model of the user dynamics, assuming that you don't have any exact track that he's following, and pass this through a single reflection multipath model, go through an estimator with the phase measurements coming in, and predict your position estimate and your integer ambiguity estimates so that you can see how well things improve if you're willing to move. And this is a little bit of the machinery that goes on inside our batch estimator. It's a least squares cost function that isolates the integer components related to those ambiguities I told you about from the real valued components related to your instantaneous position. And there are really clever techniques that you can do to isolate these two, then solve for the integers in isolation, and then pass those into these other parts of the cost function. Anyway, I won't bore you with those details, but it's really slick on the inside, and you'll see this equation come back later in my presentation when I blend this together with vision data. Anyhow, here's the upshot. This is simulation results, but you'll see that the true data results are very similar. If your smartphone is static, then your ambiguity success rate from 0 to 1 reaches a nice tolerable 90% only after about 150 seconds. The gray lines here are theoretical bounds, and the black line is the simulated empirical. So this is MATLAB experimentation. So you see that there is a long wait before you can claim you've got those integers right and claim you've got your centimeter accurate solution. But if you'll just move the phone around in ways that the estimator has nothing more than a statistical model to describe, you can bring this down to less than 50 seconds, and it crosses that threshold. So that's quite nice, and that was simulated data. Here's the survey grade antenna, and you can see that it's already doing really well. It doesn't matter if you move it, but which one won out here? Well, if I zoom in on it, I can show you that the dynamic survey grade antenna actually took longer than the static survey grade antenna. So it doesn't make sense to move the survey grade antenna, which most surveyors would have already known. But now using real data, we had a static low quality patch. Here we had a handheld dynamic low quality patch, and we got the benefit that we had predicted. It wasn't, and in fact, it fell between the lines of the theoretical bounds that we had predicted. So here we're moving from, in this case, it's not the patch antenna inside your phone, but it's an external patch. It's not as terrible as the phone antenna. Here we're going from a time to ambiguity resolution of, I don't know, around 50 seconds to perhaps one that's half that. And so anyway, there's some nice gains to be had there. And maybe I can't imagine a future where people are outside with their phone and they're all doing this. Maybe that's too goofy, but at least we'll get a paper out of this. I mean, at least we can show that if you were willing to look goofy in that way, that you could reduce your ambiguity resolution time. Another interesting question you might have is, well, what if I could tell the Kalman filter not the XYZ position of where I was moving, but at least the shape of how I moved? Could that further improve? And in fact, the answer is yes. So if you knew the profile of your motion, maybe you derive this from your camera or from your IMU, a very good high quality IMU you'd have to have, then you can further reduce this. So now we're going down from 30 seconds to about 20 seconds. It's not a breakthrough, but it does help you a little bit more. And you might say, well, how am I to know how I'm moving? What do I use for that? And that brings me to my second feature of these phones that can be exploited for better centimeter accurate positioning. The beautiful camera that they're all equipped with. High resolution, extremely low cost, and all the beautiful colors. What can we do to exploit this camera to make things easier for centimeter accuracy on your handhelds? Well, this goes back to a problem called the structure from motion problem that has been studied in the computer vision world for a long time now. This reconstruction of the Colosseum in Rome was actually done on the basis of photographs, unordered photographs on Flickr. The researchers brought them together and then ordered them, found corresponding features in the photographs, and were able to reconstruct a three-dimensional representation of the Colosseum. Now, they didn't know the scale of the Colosseum, and they didn't know its orientation in space or its location, but at least according to with reference to an arbitrary vision reference frame, they could reconstruct this. And this is fantastic stuff. Granted, it took them a day on a supercomputer to do it, but they were able to find every one of the little feature points and make the correspondence. Well, we want to do something similar with the phone, and to scale down our expectations so that we're not trying to reconstruct a Colosseum without any help, but to blend this with the GPS data so that you don't require doing your batch estimation over over thousands of photos, but rather could just take a look at the local 20 photos that you've most recently taken. And if you can connect the local 20 photos with the next 20 photos using GPS, then you can window your estimation algorithm and make it the processing possible even locally. Anyway, this is the structure from motion problem. It's a beautiful problem, and the math here is exquisite. And we wanted to leverage this for better GNSS. We call our framework VizRTK. RTK is this real-time kinematic abbreviation. VizRTK means that we're infusing visual data with the usual RTK data to improve both of them. And anyway, I hope this catches on. VizRTK, sound good to you? We brainstormed about this for some time. Here's an example. We're on the roof of the WRW Aerospace building at UT Austin, which probably the ugliest building you've ever seen, and should be destroyed and plowed under and something more modern built in its place. But I can drill holes in the walls wherever I want to. And when I'm on the roof, nobody asks any questions. So good. We're on the roof here, and my student Ken has arranged just a few artifacts in the photograph, and he's going to take some photographs. Here he is with his phone, and he's got this low-quality patch antenna on the outside. We decided not to do this with the internal antenna because even though this is only a $5 antenna, it does make our lives quite a bit easier. He's taking some photographs. These are the actual photographs taken on the phone around this set of items in the photograph. And from this, he does a 3D reconstruction. First, to determine the location of, three-dimensional location of the most salient features. This is what's called a sparse point cloud, or a sparse reconstruction. Then from the sparse reconstruction, the pipeline for this leads to a dense reconstruction. Now you can see these items. And what's beautiful here is that even though the vision reference frame is somewhat arbitrary, because we were using GPS, we can bring the arbitrary point measurements in with the GNSS measurements and solve all of this together in a joint least squares bundle adjustment, so-called bundle adjustment, plus real/integer ambiguity, real/integer least squares problem, so that you solve both the integer ambiguities and all the three-dimensional point positions at the same time in the same cost function. And so far as we know, no one has done this, and certainly not at this level. There are joint benefits to doing this. You can solve for these ambiguities more quickly than if you didn't have the vision measurements, and you provide the vision measurements more disciplined trajectories so that it doesn't diverge as you explore. Not only that, it retains the beautiful properties that made the bundle adjustment and the least squares problem interesting to begin with. Namely, the bundle adjustment remains sparse, and the integer least squares remains factorizable so that you can isolate the integer part and treat it independent. So this is the cost function that we're dealing with inside our estimator. And these are all of the different nonlinear qualities. It's a very nonlinear problem. I'll just get right to the punchline here, though. Ken, when he takes these photos, is able to develop this three-dimensional map of his surroundings in such a way that, though I didn't mention it to you before, this is a GPS antenna. And we've put some zebra striping on top so it will have easy features for the computer vision to extract. And one of the stripes coincides with the phase center of the antenna, actually the top of the antenna, which we have associated with the phase center a couple of millimeters below it. And when we do all of our processing and we ask this reconstruction, what is the XYZ coordinate of that tape intersection, the zebra intersection on the top of that antenna? It tells us, and then we make the corresponding reference to the phase center, and then we determine what the phase center is, because after all, this is a GNSS antenna, GPS antenna, right? And I can locate its phase center to millimeters if I take enough data, and I did that. The correspondence is magnificent, less than 3 millimeters, right? So using a smartphone and a cheap $5 antenna on top of the smartphone, we've turned my student Ken into an amateur surveyor where he can just go around to a park and take pictures and then go home, process those pictures, and reconstruct the park, three-dimensional, in a way that all of the feature points that he reconstructs are accurate relative to the Earth center, Earth fixed reference frame to a couple of millimeters. That's cool. That's the mapping aspect of this. But there's something that you get for free. His phone is also located in that same reference frame, both its position and its orientation, or so-called pose, as a byproduct of this operation. So he can locate his phone by taking these photographs within that same reference frame. And this is nice because it means that if you go through the process of resolving your ambiguities, maybe you have to wait for 100 seconds, maybe 200 seconds, and you finally get your ambiguities resolved so that your antenna is now centimeter accurate. Now you could walk around and take a bunch of pictures of the park or the bus stop or wherever you are. Next day, you come back and you don't have those ambiguities resolved, but you've taken these pictures and you know the feature points. Now you can just take another picture. It'll resolve the feature points that you've got against the ones that were remembered from yesterday, and instantaneously you know to about a decimeter your location, and now you can snap in those coordinates. So you can use the phone's camera to jumpstart the process of getting to centimeter accuracy. And thereafter, for as long as you have continuous connection to the satellites and you're tracking, you have centimeter accuracy. Even if the satellites go away, you can crawl along using your visual data, pulling out features and cross-referencing those. So you can even move indoors, so long as you don't explore indoors for too long, because you will diverge in that case. So I think this is great, and it's uniquely taking advantage of the features of cheap devices. Sure, they're cheap. Sure, they have terrible antennas, but they have a beautiful internet connection all the time. They have a camera that exceeds the quality of many of your cameras 5 years ago, dedicated SLR cameras, and they are easy to move. So these kind of features are hinting at this being possible even for the mass market. Now, I mentioned before that we're going to have to densify our networks in order to support this, because most of these receivers are so-called single frequency only receivers. That means you can't be too far from your reference station, and if you are, then the ionosphere and the troposphere start to play havoc with your ambiguity resolution time. This is some recent work we were doing to show that if you have spacing of about 15 kilometers between your reference nodes, then with 9 overhead satellites, you can resolve it to 90% in about 45 seconds. With 10 overhead satellites, you can do it in faster than 30 seconds. We believe that 30 seconds number is kind of magical. We believe that the Millennium generation may be persuaded to wait 30 seconds to get sub-decimeter accuracy out of their phones. Maybe we could persuade people to just hold on for 30 seconds and it'll come. And if not, then maybe some subset would be willing to wait, and they'll take pictures that get uploaded to this database, this feature database, that get downloaded to the phones when their more impatient friends decide they want to fix. So they pull their phone out, they take a picture, it makes the correspondence, and they get a 5-second fix. Okay? So that's kind of the overall goal here. We are in the process, just this year, probably by next summer we will have this fully deployed. We are in the process of laying out a dense network in Austin. Now, Nathan will tell you, that Minnesota has already a fine network, and density is quite good, 38 kilometers roughly between nodes. But for the exploratory phase of this move into the mass market, we'd like to have probably more density than we actually require. So in Austin, we're going to put up about 20 reference stations. And these reference stations are going to be built so they're fairly cheap, and they send their data over the cellular networks. And we're going to use these reference stations to determine exactly how close you need to be to support this cheap location ability on headsets, phones, and on cars. Most of this is focused on cars in Austin. And our hope is that, that we can detect a so-called direct network effect. This is one of these beautiful things where the more people are involved with your network related information distribution system, the better things get for everybody involved. This is the Facebook effect, right? more people on, the more useful it is. Well, that same network effect obtains here with RTK positioning. If we have a lot of people in downtown Austin who are using this, a few of them will have a fix, and they'll be able to provide us a better understanding of the ionospheric and tropospheric properties directly above them. And they'll be able to share that information with their neighbor to improve his or her time to ambiguity resolution. So if you got a lot of people helping, a lot of people using this, then everyone's experience is better. And we'll set up our network to be more dense than we need to pretend that some of those are users who have already got a solution, and some of them are entrants who are looking, just driving out of the parking garage and wanting to get a solution so that they can turn it over to the car and let it drive, even if it's raining, even if it's snowing, even if the roads are covered in snow. So anyway, that's where we're headed, and I'm pretty excited about this. I see it as philosophically pretty closely aligned with a lot of Max's view on how to do autonomous positioning for cars. I'll leave it there and take questions from you.
Again, for any questions, we need to use the microphone, otherwise people off in TV land, internet land will not hear the questions. So, any questions?
Just terminology. You say multipath and phase center motion. Are those equivalent, or are you saying something that they're two entirely different things when you're talking about the modeling, the residuals at the end?
Yeah, so they are two different things. Multipath is the bouncing of these signals from the satellites off of other objects in your area, whether it be the ground, a wall, and then it arrives at the so-called phase center of the antenna. The phase center is the electronic phase center, where you sense its center using all of these different signals. Now that phase center itself moves around. It depends on the azimuth and on the elevation of the impinging signals. But one of the interesting virtues of working with really low quality antennas is that they tend to be smaller. And so the phase center needs to be physically located on the antenna. That's where it's resonating with the incoming signals. So the phase center is fairly stable, even though it's a low quality antenna. Now, my friends at Novatel will tell me they spend a lot of their time improving the phase center of their antennas. But it is harder when you've got a larger antenna, because there are more places where things can resonate. And so I guess it's a bit ironic, but for smaller, cheaper, worse antennas, the phase center is not too poorly stable, not too poor in its stability.
Questions? Can I ask, when you say 30 seconds,
Yeah.
what is 0? When does it start?
Okay, 0 is when you begin taking carrier phase measurements and providing those carrier phase measurements to your RTK engine. Okay?
So let's say I have a smartphone in my car,
Yes.
right? And it's sitting on the dash.
Uh-huh.
Is it the moment I leave my garage and come outside? Or is it the moment I start the engine? When is 0 in time?
Yeah. Well, it depends on whether this ends up running as a background service on your phone, in which case, in the short term, it would deplete the battery fairly quickly. Or if it's something that you summon up as an app on demand. I think that's much more likely in the short term. If when you summon it up on demand, there will be another initialization period just for the software to boot up and for the first phase measurements to be made. But that initialization period can be made very short. We're talking 2 or 3 seconds. So the real question is the ambiguity resolution time from that 0 point. So let's just say 2 or 3 seconds. Now your phone has warmed up and it's tracking GNSS signals. The phase lock loops have locked in and are carrier phase locked. From that point, the clock starts ticking. And I would like it to be 30 seconds from that point that you can say 90% sure I've got the ambiguities.
Anyone else? Because I can ask 20 more questions here.
Well,
Anyone on the internet with questions?
A lot of people on the internet have questions.
So hypothetically, here's my smartphone in the car. It's connected directly to power. I don't worry about power. And just the time it takes to drive out of my driveway could be 30 seconds if I'm looking in every direction and doing what I should be doing. Is that enough time for everything to lock?
Well, so I should be clear here. The phase trauma experienced by signals as they enter your car is really bad. So it would be much, much better to start with an antenna on the exterior of your car. Much easier. And I wouldn't mind if that antenna was sending, you know, if the receiver itself was built into the car and sending information to your smartphone by Bluetooth. Then maybe when you're in the park having a picnic with your friend, that's when you pull out the smartphone and it's doing its own location. But don't try to do this with the smartphone in the car. We can do that with code phase positioning, but the carrier phase is more fragile. So anyway, let's just imagine it's on the outside of the car. You're backing up out of the driveway. Yeah, by the time you get turned around and you wave goodbye, you might be locked. And I always say locked at the 90% level. Some people will require higher reliability than that. If you're doing something that absolutely demands 10 centimeters with a safety of life margin, like landing a plane, like my friends at the FAA, and Demos works with them too, they start to require 5 nines of reliability. And to get there, instead of 30 seconds, it might be 100 seconds. And then you're in a different ballgame. But I think we can get to the 30-second, 90% reliability, even with cheap antennas, and I would like to make that the goal. One of the things I didn't mention here is the influence of new signals, new satellites. The more satellites you've got overhead, and you can kind of see this here with this plot, this was with 9 satellites, the blue line, and we got to the 90% level, this horizontal line, we got to it in about 40 seconds. Well, just with one more satellite, we were able to cut that down to 15 seconds. There are diminishing returns here, but every new satellite makes your solution more robust and snappier. And you might think that this is a little counterintuitive because every new satellite also comes with its ambiguity that has to be resolved. So you're adding data, but you're also requiring more of the estimator. Well, but turns out in the least squares problem, in the integer least squares problem, that is a welcome addition. Go ahead, challenge me to find that ambiguity, but just give me the data. And when these new satellites are being launched by the European Galileo system and the Chinese BDS system, in China right now, you can look up and see 15 overhead satellites between GPS and BDS and a little bit of Galileo. When that happens here in the United States over the next couple of years, as Galileo increases the number of satellites and BDS increases the number of MEO satellites, medium Earth orbit satellites, you're going to get to a point where it becomes reliable even for single frequency users. 15, 16, 17 satellites. This will snap in more quickly. And I'm looking forward to that. I think that's really the inflection point that makes this possible. And if I'm one of the entrenched players, Trimble or Novatel or Javad or others, I've told them that if I were in your shoes, I would go to the satellite launch areas and I would chain myself to the launcher and you say, don't launch this, you know, kind of like the old environmentalists did with the nuclear facilities. Don't launch it because every new satellite that goes up there undercuts their business case. They've been selling these things at $5,000, $7,000 receivers, and they've been doing it because the only way to get the reliability you needed was to have all their fancy techniques on the inside and a lot of intellectual property and multiple frequencies. But with more satellites, it's just more forgiving. And that means the lower cost receivers can play.
And so when you first showed that cell phone, you said you were using an off-board clock.
Yeah.
Is everything else after that using a more fancier clock that you showed, or is all of it just using the clocks that are within the...
No, we were always using at least TCXOs. Now the clocks inside the phones are also TCXOs, but they're kind of on the low end TCXOs, temperature compensated crystal oscillators. So we have, by now, pretty good results even with the lower cost TCXOs. So I'm talking about a $1 unit, a $1 to $3 unit. The ovenized crystal oscillator we used the very first was a $1,000 unit. But we've now had, in just the last couple of months, lots of practice with the $1 units. Frank Van Diggelen in our community has given me a couple of his latest generation Samsung phones. He's from Broadcom. They make the chips that are inside of many of your iPhones, many of your Samsung phones for GPS. And his most recent chips will produce phase and code phase data. So he can actually write a Rhinex file to the phone for me to extract. And we've got a paper for plans on this, where we're going to write about how much you can do with the internal chipset, internal antenna, and also internal clock. But my strong suspicion is it's not going to be as good as our results, because I was able to use my software-defined receiver and fancier techniques, even vector processing, to improve my reliability. Nonetheless, I'm happy to report the results if they turn out to be good or bad. You know, we'll see.
For using the photos to improve your positioning, how much do you rely on having a good three-dimensional, basically, base map of whatever the objects are that you're identifying? You know, if you only had pictures of an object from a few angles that are all on the same side, how much is that going to affect your ability to improve your accuracy?
Okay, so there are actually two questions here. Let me treat the jump start case separately. Remember, the jump start case is when somebody has taken some photos, maybe you, somebody else, of the area, and there are feature points that you can see today that were also registered yesterday or the week before, and registered with a centimeter accurate solution. In that case, you only need one photo. You need to stand somewhere around the area that was mapped, and you take one photo, and it makes the correspondence with those feature points, determines the pose of the camera, and you're in. If you'd like, you can take multiple photos to make the solution more robust, but it's not required. So for that, you do need the prior map. Somebody had to have laid that out. But it's a sparse map. I want to emphasize that you might be only dealing with 100 point features in the vicinity, and only 30 or 40 of them that show up in your photo. Okay? As regards to the ability of the camera to aid you in an unknown environment, that is still possible. The idea here is that all you need to do is kind of figure out what the shape of your motion was when you were dithering the cameras or dithering the antenna. And for determining the shape of your motion, you can do that in the camera's reference frame, its arbitrary reference frame. And what you'll have is a trajectory that is connected by a similarity transform to the trajectory as it would be represented in the GPS frame. A similarity transform, a translation, a rotation, and a scale factor. But your estimator, the one that I showed here, this joint estimator, basically estimates all of that at the same time. And so the picture that I showed here, this guy here, motion profile aiding and no motion profile aiding, was one where we just told it the shape, and I think we told it the scale factor, but we didn't tell it how it rotated or translated. And yet it was still able to improve its time to ambiguity resolution on the basis of that shape. So, of course, if you take a picture and you know where you are by the basis of that picture, then you don't have to ask yourself where you are. And things resolve very much immediately. But here, it's just, the shape itself is good enough to constrain, anytime inside the Kalman filter, if you can just constrain its state space, whether in time or instantaneously, that's a benefit.
Last question.
I was wondering if you'd have made any assumptions or done any testing with the L5 signal for GPS?
Yeah, so we hardly touch L5. I mean, some of our receivers produce it. It's nice because it's wideband. It's nice because it's very strong. It's a couple of dB about 3 or 4 dB stronger than even the L1 signal. But I guess because our emphasis is on cheap receivers, we're looking at the single frequency receivers, and sometimes we consider dual frequency with L1 and L2. L2 is a narrower band signal, so it's easier to get into the cheap receivers. You don't have to be sampling it so quickly. So if we want to splurge, we only splurge at L2. We don't go to L5. If you want the full McCoy, if you want a receiver that can handle everything in the sky and every signal, you go to Trimble. And they'll sell you it, and they'll smile and charge you the $10,000 that they charge you. But we want to ask, what can you do with $10?
Will you join me in thanking Todd Humphreys for a really interesting talk?
Sure.
And just want to let you know that next week, Linda Boyle, she's a professor and chair of the Department of Industrial and Systems Engineering at the University of Washington, will be here talking on the modeling the effects of drivers' adaptive behavior on system safety. So that's next week, same time, same place. Thank you. Thank you.
Thanks, Matt. Well, it's nice to be followed up by such a nice